welcome back to the course on architectural design of ICs. So, in the last class we have seen that means the carry ripple adder, how we can design this ripple carry adder. Then from that particular point, how we can generate, or that means what is the logic behind generating the carry and then propagating the carry. That means the main problem with ripple carry adder is that unless and until the carry is available on the that means subsequent stages, it cannot start its computation. So, that is the main problem, and that is why we are getting a longer critical path if you are considering the bit, that means more of the bit for addition operation. So, that is why what we have seen, we have studied the operation table, and from that operation table we have seen that okay, the carry and the carry is basically propagated and the carry is being generated based on the corresponding input bits, which is A and B. Okay. And how they are related, that we have seen in the last class. So, today again we will see another, that means architecture which is carry skip adder. Okay. So, carry skip adder, the by its name it says that means we can skip the carry. Okay. So, where we can skip the carry, or how we can skip the carry, or what is the, that means intention, or what is the, that means usefulness of skipping the carry whenever we are performing the addition operation, that we will see in this particular lecture. So, here you see the first the upper architecture is nothing but the ripple carry adder. But here if you just see, there is I have put one multiplexer over here, and that the input Ci, that means the whatever carry is coming over here, that is basically connected at this particular point of the multiplexer. So, that means, and what is the select line of this? The select line of this is this P0, P1, P2 ANDed operation of P0, P1, P2 and P3. So, means what? So, what is P0 and G? This P0 and G, this P and G, that is the logic for propagation of the carry, and G is the generation of the carry logic. Okay. So, now if I just put this particular, that means if I just that means this full adder cell, if I just generate using the previous architecture, then at the final level or at this particular stage, I put 1:2 multiplexer, where if this all this propagated carry is 1. So, at that time it will select the carry input of this C I 0 as the output of C 3. So, here the idea is that if P 0 and P 1 and P 2 P 3 all are 1. So, at that time C O 3 will be the C 0, else kill or generate the corresponding carry. So, if I just want to design one n bit carry skip adder, so at that time if I just make one group of k bits, so at that time I need n divided by k number of groups. Okay. So, n divided by k number of groups. So, these groups, if I just write it like Z0, Z1, Z R minus 1 and ZR, where R is the number of groups, and each of this group is basically the carry skip adder, which is basically considering of k number of bits. Okay. So, then this carry, that means the corresponding carry out, that is basically or with this in each of these stages, and it is being, that means the sum is generated from each of this group, where this is A0 to AK minus 1. Okay. That means, if I just consider, if I want to design, suppose a n if I consider of 16 bit, okay, and k if that is of 4 bit. Okay. So, that means at that time I will have r equals to 16 by 4, that is equals to 4 number of groups. Okay. So, each of these, then this will be A0 B0 to A3 B3. Okay. So, that means here it will be A3 B3, this will be up to A0 and B0. So, here up to, that means how much I will get, that is S0 to S3. Okay. And this line is basically the corresponding that P0 value, which, that means this is the corresponding P0 value which I am getting over here, and this is the G0, that means this 4 of this I will get, and this is basically OR with, in each of these group bit is basically then OR. Okay. Now, if I just go to the, that means then if you just consider, since the C into C out represent the longest path in the ripple carry adder, an obvious attempt is to accelerate carry propagation through the adder. Okay. So, this is accomplished by carry propagate PI signals within a group of bits. If all the PI signals within the groups are set to PI equals to 1, then the condition exists for the carry to bypass the entire group. So, in the last, that means in the last class what we have seen is that, suppose I am having this. Okay. So, this is my, suppose P0 and G0, then this is P1 and G1, something like this, which are connected. Then if this is the Ci, then that will be ultimately, this is the P0, P1, P2 and P3 signal, which is basically selecting this. If all the bits are 1, so at that time it is selecting this CO final out, C out equals to this Ci. Okay. So, considering this C into C out, considering this C into C out. Now, if I this, each of these is basically nothing but that carry, this 4 bit carry skip adder, if I consider a k equals to of 4 bit, right. And then this we have divided it like this. So, the final C out is basically, now we have find out something like this. Okay. So, now the critical path will become, or the critical path now it will traverse from this particular point to this. Okay. And the total delay will be 2 k minus 1 plus n by 2 minus 2. That is the, where k is the number of, that means bits per group, and n is the number of bits what we have considered. So, carry skip adder divides the words to be added into groups of equal size of k bits. The basic structure of n bit carry skip adder we have already shown, and within the group carry propagates in a ripple carry fashion within the groups. Okay. But in addition, an AND gate is used to form the group propagate signal. If group propagate signal is true, the condition exists for the carry to bypass the group as shown in the corresponding slide. The maximal delay of the carry skip adder is encountered when carry signal is generated. Carry signal is generated in the LSB position, rippling through k minus 1 bit position, skipping over n divided by k minus 2 groups in middle and rippling through k minus 1 bits of MSB group and being assimilated in the nth bit position to produce the sum of Sn. Thus, carry skip adder is faster than ripple carry adder at the expense of few relatively simple modification or relatively addition of few extra gates, okay, or the multiplexer or extra hardware. If I say the delay of the carry skip adder is still linearly dependent on the size of the adder of n. However, this linear dependency is reduced by a factor of k. Okay. So, why this factor of k it is reduced? Because we have already divided by n divided by k, and here you see as this depends on k, and here it is not that much linearly. That means, in ripple carry adder how it looks, that means increases, that is the delay will be like n minus 1 number of stages I need to cover, but here I do not need to cover that n minus 1 number of. So, here the delay will be n by 2 minus 2 plus 2 into k minus 1. Okay. So, the delay has been reduced, or the critical path has been reduced by a factor of 4, if I consider k equals to 4. Okay. So, then if you just see the curve, so at that time this ripple carry adder, this is the, that means the corresponding values of n. Okay. So, this and this is the corresponding critical path. Okay. So, if I just plot, whenever we are considering this, we are increasing the number of stages. So, the critical path also increases linearly along with this. But for bypass adder, what happens? Initially the delay is more. Okay. If we consider lower number of that means n, but for more number of n, as this has increases, so at that time it started bypassing, and then it is basically the delay is reduced for more, if we consider more number of bits. So, that means what I can say, that when this, what I said in the previous slide is that this carry skip adder is linearly dependent on the size of the adder n. However, this linear dependency is reduced by a factor of k. So, that means for when the smaller values of n, at that time I will not get that much of benefit in carry skip adder, but whenever we will use, or whenever I need to design the n is as large as possible. So, at that time, as I can reduce the delay by a factor of k, or so that means the linear dependency at that time it got reduced, and I can get the, that means the corresponding delay something like this. So, that is why you can use carry skip adder for larger number of addition operation where it requires. Okay. So, then next what we will see? We will see another that means addition operation, which is variable block adder operation. So, variable block adder operation means, so here we are considering what? We are considering the k equals to, that is fixed, whether that is 4 or 3 or 2 or 6, something like this. But if I just vary the bit width, that means if I vary the k, at that time what will be the effect of that? Okay. So, in the previous slide, if you just see that, here you see the maximal delay of carry skip adder is encountered when carry signal is generated in the LSB bit position. Okay. So, in the LSB bit position, if it that means generates the carry, so at that time it has to ripple through k minus 1 bit position, and skipping over n minus k by 2 groups in the middle, rippling through k minus 1 bits of the MSB group and being assimilated and the nth bit position to produce the final sum. Okay. So, that means in the carry skip adder, if I got that means in the LSB position, if I got 1, so at that time it will that means it has the longest path to be covered. Okay. But based on that, we are basically trying to develop this variable block adder. Okay. So, in the variable block adder, what it says, in the variable block adder, what it says that in the that means LSB position, if you see, it has only lesser number of, that means in the LSB and in the NMSB there are lesser number of groups, and in the middle position there are more number of, that means groups. That means here we are skipping, actually what, whenever the carry is generated, at that time we are skipping the next thing. So, that means the skipping of this, we have to generate the carry in each of these groups, right. So, and that carry is basically skipping based on the, that means whenever this carry is generated at this group, so based on the logic it can skip that particular logic as it has been discussed. Okay. So, now whenever if we consider more number of bits to compute the carry over here, final carry over here, that will take time. So, that to reduce that, what we are doing, we are taking the minimum number of, that means bit at this and the MSB position, and then in the middle we are considering more number of bits. Okay. So, that is why you can see that this is the C in. So, this is for, so this is for this particular group, it can skip, then it has been considered more from this particular stage. So, it can skip up to this, and in this particular, that is again more from the P1. So, it can skip over here. So, in this fashion it can ripple, this is the carry signal path, and finally, you can get the final C out signal. Okay. So, this is the, that means the carry is in that means the difference between this earlier architecture and this architecture is that there we are considering the k fixed to each of the, that means this grouping, but here the grouping is being dependent, or the grouping has been done considering variable of k, where the middle position is considering more and the LSB and MSB position that are considered as low as possible. Okay. So, the idea behind variable block adder is to minimize the longest critical path in the carry chain of carry skip adder, while allowing the groups to take different sizes. So, what I said, that k that can take to different size. Such optimization in general does not result in an enhanced complexity as compared to the carry skip adder. A carry chain of 32 bit variable block adder is shown in the earlier that means slide. The first and the last blocks are smaller and the intermediate blocks are larger. That compensates for the critical paths originating from the ends by shortening the length of the path used for the carry signals to ripple in the end groups, allowing the carry to skip over larger groups in the middle, and there are two important consequences of this optimization. Okay. The first, the total delay is reduced as compared to carry skip adder, and the second is that the delay dependency is not a linear function of adder size n as in carry skip adder. This dependency follows a square root function of n instead. Okay. And it is also possible to extend this approach to multiple levels of carry skip, which represent a linear programming problem that does not yield a closed form solution, and the speed of such multiple level adder surpasses that of fixed group carry lookout adder. It also exhibits the low power, low area and power consumption while retaining its speed. Variable block adder has the lowest energy delay product as compared to the other adders in its class. Okay. So, that means, if you see that here for these particular things, if I can skip, this is for 3 bit, this is for 4 bit, if I consider this is for 5, in the middle I can skip more, which is 6, then again 5, 4, 3 and then 1. Okay. So, that means I can skip the corresponding values in this fashion. Okay. That means how we can that means in the middle position we can skip the more. The point is that we can in the middle we can skip the more, or we can take the values of k more in the middle position and lower just correspond or just that means besides of them. That means in the middle it is more, then the side of that 2, that will be just lower than the middle one, then after that again lower than the previous one, then something like this we just follow to the LSB and MSB side. Okay. So, for any point to point delay here, that is if that is 9 delay as compared to 12 delay, which is reduced or required for carry skip, that k group adder we have designed in the earlier case instead of variable. So, in variable we will get 9 delay, whereas in carry skip adder we can get, we get that is 12 delay. Okay. So, that means if we consider this particular example. So, here at this, if you just see, that means here this is basically a rippling for this, then for this. Okay. So, then this is one histogram of how, that means this how this is basically changes. This carry chain block size determination for a 32 bit variable block adder, that means how we can define these k values. Okay. That we have to do some linear programming for that. That means for what is the, that means the size of k by which choosing the size of k, so that I can get the delay value as low as possible for variable block adder. Okay. So, if you just see that here this n equals to 64, okay, and how for x 1 and x 2 they are being selected as 4, okay, and for x 2 and for x 2 and x 7 they are being selected as S 7, x 3 and x 6 they are as 10, and for this x 5 which is the middle of this, that is x 4 and x 5, that is selected as 11. So, that means for the lower that means this position and this particular position, they are selected as low as possible, which is the 4 1. Okay. So, the delay is considered, or the delay which is the, that means the considered here, which is the C 1 plus mod of C 2 n plus C 3. That means, here this is this the group corresponding delay for carry 1, what is the delay, then for carry 2 what is the delay, for carry 3 what is the delay, that are basically considered here for computing the corresponding critical path. And here you see this is the square root the delay is basically not dependent on the linear dependency, it is not there, it depends on the square root operation of n. Okay. So, that is the beauty of variable block adder. And here you see that means another example where you that means I have chosen more number of that means group which is like x 1 to x 15, okay. And then that means if I consider, I can just make it like 1, 2, 3, 4, 5 also I can make, or I can do what? I can just make another x 1, x 2, x 3, x 4, x 5, x 6, x 7, something like this. Means what? This is the bigger group, and then the bigger group again that can be, that means divided into two other group. So, if I consider this as, let us consider this as x 1, then y 1 which is the bigger than this, that again can be divided into subdivided into two other, that means group, which is x 2 and x 3. Then y 3 that has been divided into three other group, which is x 4, x 5 and x 6. Then y 3 that has been divided into three other group, that is x 8, x 7, x 8, x 9. So, something like this, in this manner we can just take different combination of groups and we can get, or we can, that means in which particular combination I am getting the minimum number of delay. So, we will consider that. So, that means that as the final one. Okay. So, that is why it is a dynamic programming problem. So, if I compare the delay of variable block adder for this carry skip adder, if I consider this n as 16 and this is for carry look ahead adder. So, for 32 the delay in carry skip adder, that is 9, and in this carry look ahead adder is 8. So, this is the delay comparison with CLA for the method used in the earlier, that means what we have seen, that means in this fashion, and or in this fashion. So, and if we just do that grouping in this fashion, then that is that the delay for the same thing, the delay will be 5 and 6 over here. For 32 it will be 9 and 8, for this it will be 7 and 8, for 42 it will be 12, 10, for this it will be 9 and 10, for 64 it will be 14 and 10, it will be 10, 10. So, that means this particular, that means this grouping is more, I can get the delay more reduced in comparison to the architecture or the, that means grouping like this. Okay. So, this is that means this is the that delay comparison we have plotted. So, this is the variable block adder, this is the blue one is the CLA and the red one is the that means variable block adder multi-level, what I discussed in the last. So, that means here you see this is as you increase the size of n. So, this has the reduced delay in compared to the other two. Okay. So, thank you for today's class. Again we will see more adder architecture in the later or in the future classes. Thank you.